First of all, I would like to thank you for the invitation. There is a slight correction in the title. I dropped the word saga. You have heard yesterday the definition of saga, and for me it has a connotation that the ancestors tell you a story, you tell the story to somebody else, and so on. You are very fortunate because you to some extent can hear the situation from the horse's mouth directly. I was there in the center of action even before the word neutral current has been pronounced. So this is Gargamel in its full glory. You can admire it now in the CERN ground. It was 45 years ago, it was in extremely good shape. It was conceived by André Lagarrigue. He is really the father of the bubble chamber. It was running from 1961 up to 78 when it failed due to a crack. At the end of 1971, there was a historic moment. Some theoretician, Gaillard, Zumino, and others came to Gargamel to tell them that there is a unique situation, namely the existence of a model which combined weak interactions and electromagnetic interactions. And in there was the photon, of course, the W, but also a new intermediate vector boson. And 't Hooft at this year proved that this model is renormalizable. The key element is weak neutral currents. So they were telling us you have a historic chance to prove or disprove the existence of a new type of process where a neutrino-induced interaction leads in the end, in the final state, either to a lepton or to a hadronic state. At that moment, there were two detectors. Gargamel at the CERN PS and the experiment E18 at NAL, which is now called Fermilab. You can see the bubble chamber within a lot of heavy material. Indicated here is the fiducial volume of the heavy liquid and the coils and the yoke. And the neutrino beam is coming from the right and passing through a very thick iron shield. On the other side, the American experiment consisted of a liquid scintillator calorimeter and a magnetic iron spectrometer. Gargamel and the American experiment, the HBW collaboration, were both approved 1970. They had a priority on the nucleon substructure, which was recently discovered at SLAC. On the other side, the search for the W by looking at the energy dependence of the cross-section. Data taking started at 71, 72 in both cases. The beam was in the CERN and wideband horn focus beam. On the other side, it was a mixed beam. The energies are different by a factor of 10. In the bubble chamber, of course, everything is recorded, whereas for the counter experiment, they have to define triggers in order to select the interesting events. I mean, you note that the priority it did not include neutral currents. This was coming only 1972. And in looking, obviously in looking for a new effect, you have first of all to define a signature to characterize the new effect. But then the most important thing is to investigate all processing. The accent is on all. In practice, of course, it means that you never can be sure to have all. So you have all which you know, which you could think of. Then at the end, you can make a claim of a discovery once the number of signal events is much bigger than the number of background events. The situation in the Gargamel case was very simple. there is a neutrino interacting and producing an event inside the liquid consisting of hadrons only. The background, which was long known already in the experiments beforehand, was an upstream neutrino interaction in the shielding, generating a neutron which enters and gives the same configuration. So that is a famous neutron background problem. For the counter experiment, the situation is such that you request a big amount of energy deposited in the target calorimeter and no muon in the muon spectrometer. The background obviously are the charge current events where there is a muon, but the muon escapes detection. Now, for the Gargamel experiment, we were in a very happy situation because before the experiment started, we had to define scanning rules in order to ensure that each of the 7 laboratories provides data with the same quality. We have defined 4 categories: events with a muon candidate, events with identified hadrons, events which consisted only of 1 or more low-energy protons, and finally events which consisted only of electrons and positons. Obviously, the normal, known neutrino interactions were in class A. However, also neutron-induced entered into that category, namely in those cases where a final state, pion or kaon, simulated a muon. But neutron-induced enters into class B in those cases where all final state particles were identified as such. This class was very important because the class A necessarily had a neutron background, and this background could be subtracted just by using the events observed in class B. Now, at the moment when the challenge came to look for neutral currents, we were in this excellent position because if such events exist, they must already be included in the class B events. So we could immediately start with a search for this. This was in summer 1972. In summer 1972, and within about 9 months or so, the analysis was done. During that time, a very exciting leptonic neutral current candidate was found. It consisted, it is now in all the textbooks, you can see an electron identified twice by change of curvature and by radiating photons. The energy was about 400 MeV, and it was going in forward direction. The fortunate thing is that it was observed in the antineutrino beam. Therefore, the background of nu E was very small. It consisted of an electron and a proton, but it simulates that process only if the electron is going right in forward direction and if the proton is unobserved. Therefore, this background was extremely small. A nice neutral current candidate is seen here. You can see that it is a 3-prong event with 6 GeV, so a quite high energy given the fact that the neutrino beam had a typical maximum energy, a typical mean energy of 2 to 3 GeV. You can see that all particles, the tracks of these particles are all interacting, therefore it is a unique case. Now, in March 1973 was this famous meeting where Lagarigue presented the situation. He was in a rather euphoric state for very good reasons. There was this unique electron event. There were unexpectedly many candidates without muon, and there was a subsample of charge current events where the muon is ignored and the same criteria are applied to the hadron state. The expectation was quite spectacular. If there is a dominance of neutrons, then they would follow an exponential distribution. The typical interaction length is 70 centimeters, so 70 centimeters is small compared to the extension of the chamber of about 5 meters. Therefore, if there is, in the second part, if there are events left, this would be the indication of a new effect. Now, this here is the situation of the measurements. At the left side, the neutrino data, on the right side, the antineutrino data, and plotted along the direction of the beam and radially. See, if you interpret that, then you have 3 arguments in favor of the events being due to a neutrino origin. If you look at the ratio of neutron currents over charge currents, you can see here and here and here, it is flat and big. Secondly, the neutron current candidates look neutrino-like, and the neutron current candidates do not look neutron-like. There was a Monte Carlo, a very simple-minded Monte Carlo by the Orsay group, which disfavored neutrons and therefore contributed to the excitement. So somehow the people there had the impression, now we have a discovery at hand. Unfortunately, there were 2 bad guys making 2 critical counter-arguments. One was neutrons may make cascades. So in the shielding, where you don't observe what is happening, the neutrons could easily have made a cascade, and therefore the number of events can be much higher. You can see here the setup in terms of interaction lengths. The amount of interactions per interaction length is about a constant. And you see then that it is not just from the first layer that the neutrons would enter, but they could come also from deeper layers, and therefore there is an uncertain amount of increase for the background. Another argument was the neutrino beam is not just hitting the front of the bubble chamber, the entrance window, but it is extending, and therefore you have lots of events, I mean, really a huge amount of events at the side. As soon as there is an interaction sending a neutron in the direction of the chamber, you obviously fill that and you get a flat distribution also from the background neutrons. In conclusion, there was no distinctive feature left, and the neutron background could be dangerously big. This is a usual dilemma, being first and being right. So at the end, the decision was to make an absolute prediction of the number of background events in order to be sure that there are indeed events left which cannot be due to neutrons. The neutron background calculation requires 4 ingredients. The first is the matter distribution. Now, this is very complicated but known, and it could be implemented in a program. The other ingredient is the neutrino flux. That was measured and very well known beforehand. The third is the dynamics of the final hadron state. That could be deduced directly from the observed events. And last, and most complicated, one had to have a model how the hadrons are transported in matter. This required a cascade model. So the situation looked rather hopeless at the beginning, given the fact that this calculation should be done within a few months. The real breakthrough came when we recognized that a final state, pion or kaon, has never enough energy to produce in the interaction a deposition of more than 1 GeV, which was the selection criterion for neutron current candidates. Therefore, the situation was left with a linear problem where only the neutrons or protons can carry the cascade. And what was needed then was the elasticity distribution, which tells you how much energy is deposited and how much energy is carried on by the secondary proton or neutron. So the conclusion of that is the program contains all the ingredients and it has no free parameter. So even the information needed for the elasticity could be deduced from existing proton data. A neutron interaction can appear in two ways. It can be the end of the cascade, namely the upstream charge current interaction producing a neutron which enters and produces the event. The other is the beginning of the neutron cascade, namely those cases where you have a charge current interaction inside the bubble chamber and an energetic neutron which interacts inside the bubble chamber, and therefore you have here a way of seeing what happens in such, what happens really inside the non-visible part of the shielding. So the idea was then to predict the ratio B over AS, where you make optimal use of the data and you the ingredients which you needed had rather little influence except for the cascade effect. Now, the worst assumption you can make is by saying all the events the neutron current candidates observed are indeed background. In that case, the number of background events over the number of associated events is equal to the observed candidates, 102, divided by 15 associated events. So you end up with a factor of 6 about. On the other hand, the cascade program predicts that this ratio is 1 plus or minus 0.3. Therefore, it was a very eclatant discrepancy, and you could reject the hypothesis and claim to have a new effect. The same is valid also for the antineutrino data. Another way of looking is to reconstruct from the final state the direction of light. Then you can measure the flight path and the potential path and apply the classical Bartlett method to deduce the apparent interaction length. And 1 over that quantity is very near to 0, therefore typical for neutrinos. You can see here what happens for charge current events, which are definitely neutrino-induced, then the neutron current events, and last the associated events. You can see that the neutron current events are very close to them, indicating that the background is small. So at the end of July, the paper was sent off, and these are the two title pages for the lepton event and for the hadron events. Unfortunately, already some of our colleagues deceased. It was already in 1975 that Lagarigue deceased, followed by Rousset, Musset, Rollier, Weissner, Schulze, Lanske, Nguyen-Kak, Camerini, Fry, Waxmuth, Natali, Bullock, and just recently Violette Brisson. Now, we were all in a quite happy state until the conference at Bonn, the electron-photon conference, where the results were presented to the community. It was for the first time that neutrino physics was admitted at this conference, and it changed name from that moment on and became the lepton-photon conference. Gargamel presented its results, which were already published, and as a last-minute contribution came a paper from the HBW experiment, which was included in the Gargamel talk, and compared, and agreement was found between the results. In addition, there were from the argon group, from the 12-foot bubble chamber, observation of the exclusive one-pion channel. There was also made a first attempt to compare the data with theory, and out of that came a sin² theta value around 0.3. Xi and Yang at the end of the conference announced, you can quietly go home and be happy, we have a new effect, neutral currents exist. Now, this happy state was very soon interrupted. There were prominent physicists criticizing Gargamel and saying, you have only rediscovered the neutron. The arguments which were brought forward could be easily rejected. No one has ever thought of a new argument which the collaboration itself had not yet anticipated and discussed thoroughly before publication. The really bad stroke came when the rumors from the States came along saying that we have now new data with our modified apparatus. We have modified it because they wanted to have a better detection efficiency for muons. So they have introduced a small plate, 13-inch iron plate, so 30 centimeters. And indeed, they could say the effect is there. We have a much better detection efficiency. What they did not think of is that there are hadrons which can penetrate, and the punch-through simulated, of course, events, and this way they lost the neutral current events. However, they needed months in order to recognize it. For the moment, it was the claim was Gargamel is wrong. Neutral currents don't exist anymore, and you are in trouble. So also the CERN directorate got worried. In this situation, there was only one way out. We had to give a proof of the ingredients which were necessary in order to make the prediction. Now, I would just like to give a short history of the publications. On 17th of July, Ruppia was approaching Lagaric saying, we have about 100 unique neutral current candidates. How about you? When at the 17th was 2 days before the open presentation in the CERN auditorium. At that moment, the Gargamel collaboration was sure and convinced to have made the discovery. However, it was not yet published. Then Ruppia also indicated that we are about to send a publication for that, and this was submitted in August 3rd. This same paper was also submitted to the Bonn conference. The paper was then slightly revised because the referee had some comments. However, the collaboration decided to postpone the publication because they had already modified their detector and wanted to have more data, better data. However, during that case, it turned out that they lost the signal, and there is this letter dated the 13th of November, where the collaboration sent a letter to Lagaric telling them that they have no longer an effect. They quote a limit of 0.02 consistent with 0. Finally, they have understood that the problem is due to punch-through, and they have then written another paper dated February 25, submitted to Physical Review Letters, which appeared then in April 1974. So you have here appearance, disappearance, appearance, and this gave rise to the statement that they discovered the alternating neutral currents. Now, this experiment to Gargamel consisted of sending proton pulses of fixed energy into the bubble chamber. They were chosen to have 4 GeV, 7 GeV, 12 GeV, and 19 GeV. And here you can see a very beautiful case of a 7 GeV proton entering, interacting, and then producing a neutron cascade. In measuring in these events the first interaction, you get the information about the apparent length in the bubble chamber, and by measuring the last, you can get the information about the effective cascade length. The program, in order to calculate the neutron background, was then applied to the conditions of this special experiment, and the prediction had to be made before the experiment was done. So this is a real proof, yes or no. You can see that the apparent interaction lengths in the chamber turned out to be slightly bigger than 17 GeV, as you can calculate from the Rosenfeld tables. It is something like 80 or 90 centimeters, and it is flat energy independent, whereas the cascade length is increasing with energy, as you expect. The agreement is very fine, so all aspects of the criticized cascade program were confirmed. The situation clarified in spring, and this was a real happy end. Gargamel had doubled its statistics and found good consistency with the already existing data. The neutron background accounts for about 10% and has been proven in 2 ways, by the absolute calculation and by this internal method, and the cascade effect itself has been experimentally confirmed. The ANL collaboration had now neutron pi plus and proton pi zero exclusive processes clearly observed. And there was a new experiment, the Caltech Fermilab experiment, in a narrowband beam. They have clearly observed the existence of neutron currents. And finally, also the HBW collaboration confirmed the existence. So the community was finally convinced that weak neutron currents exist and have accepted it. The impact of this discovery was really huge. All major laboratories have now defined a long-range program to investigate this new force. This was the beginning of the electroweak way, which ended up in the standard model as we know it today. It was a breakthrough to gauge theories. Monthly new models were proposed and tested. The frontiers were pushed very much in both in energy and in precision, giving rise to new detectors, to excellent new large calorimeters. Large collaborations were forming. Big computing was started. I just mentioned 2 immediate applications. One was already mentioned yesterday by Adam Burrows in the context of gravitational collapse. Another one, in 1976, was the observation that now within this Glashow-Salam-Weinberg model, you can predict the mass of the W. Knowing the measurement of sine squared theta, you predict that the mass of the W is 17 GeV or so. This was really an important statement, because all the previous attempts to obtain an information about the W by looking at the deviation of the linear cross-section was now impossible. There would never be an experiment of this type. Except perhaps 20 years later by Hera, where the energy was big enough to see really the W propagator. At that moment, the P-bar-P experiment was proposed and realized at CERN as P-bar-P collider. So at the end, I would like to say that Gargamel was an excellent collaboration with an excellent pioneering spirit. It was my first big collaboration. Now, of course, big in today's standards is no longer correct. It was live without email, without these big, excellent computer codes, without laptop, however, with punching cards, handwritten slides, and so on. I should say that it was a great honor for me to have been a member of Gargamel and to feel the responsibility in the context of a discovery. Thank you very much.
So maybe I have one question. Is you discussed the process of understanding this data and the discussion we had inside the collaboration, yes. But have you had also similar exchanges about, in addition to formal letters, with the Fermilab collaboration, the HPV?
Not officially.
No.
But
there were exchanges about methods, backgrounds.
No. I mean, subcutaneous. One knew roughly what was going on. Subcutaneous, there was some exchanges, but on a personal level, and more like gossiping.
And is there any hint about why they changed this? What was behind this?
Well, we understood, of course, immediately when we knew about the fact that they lost the event because they had a small iron. You understand now? We have made all these calculations before we during our evaluation of the Newton background. We knew what punch through would do. Since we have the transport of the cascade, we have the full calculation done. So, if they had asked us, we could have told them that 30 centimeters is by far not enough. And it took months for them in order to realize that they need the order of a meter in order to suppress, to hinder hadrons to punch through and therefore simulate a candidate.
But as you already pointed out, you had the electron event, right? The leptonic event, which doesn't have these problems. So how did
No. But of course, people were saying one event is no event. Well, the situation was very interesting. We had this one event, therefore we could calculate the cross-section. And then half a year later, they said, oh, your cross-section is already at a factor of 2 down. And we had to wait 1 year for the second event and another year for the third event. So, but then later on in the 1985, in the charm experiment, you had 1,000 events. 1,000.
Michel Cribier-Saclay, I don't understand how many people were really making the analysis in Gargamel. It's what, less than 10 people? Or?
Well, the Gargamel consisted of 57, I believe, members. And all asked nasty questions inside the collaboration. And we have done this fight inside the collaboration before going to the public.
Vigneault, APC. Gargamel has not been built to discover
No.
neutral currents. When the collaboration, you mentioned that the theoretician influence was important to decide, but was the collaboration ready to go directly to neutral currents,
That's right.
or there was a discussion?
Yeah. Well, I can anticipate there was 1968 was a big meeting in Milan, a 2-day meeting where the physics of Gargamel was discussed. During that meeting, the word neutral current was not pronounced. So it was a year or 2 years, no, 1 year after the discovery of the substructure, and I mean, everybody was saying, this is our chance to find out whether the neutral current, the charge current of course, would detect the same kind of substructure inside the proton. So the focus was immediately put on that, and all the scanning was done in order to get results, which in fact was also the case. It was only at the moment, I mean, at least the experimentalists were not aware of the Weinberg model nor of the calculation of 't Hooft. However, as soon as it was pronounced and people were coming, wake up and look that you have here a historic chance. At that moment, we immediately started, and we could do that because the events were already in the class B events, which which we had necessarily to have in order to be able to subtract the Newton background from the charge current events. I mean, that was a procedure which was already known in the previous neutrino experiment. So for us, we could immediately start from one day to the next day. And the decision was taken in a meeting in Paris in spring, and there the most important result was that we select the candidates with a cutoff at 1 GeV in order to suppress the very well-known Newton background.
Kozanetsky-Saclay. I vaguely remember that in the thesis of, over here, Dieter, that in the thesis of Jean-Pierre Vial, which was on some, I don't know which neutrino bubble chamber experiment,
yes,
Gargamel also, there was a 30% background that was not understood, and that if that had been, if people had recognized at the time what it really was, the neutral current discovery would have happened earlier. Now, something similar was mentioned by somebody yesterday, and I don't know whether it refers to the same occurrence. Does that tell you anything?
You mean Cecilia's remark about the BNL experiment? I mean, they did not have an energy trigger. And I mean, the same problem was also with the experiment at CERN 1963. They had these events, obviously, but they could not make use of it because they required right from the beginning the presence of a muon.
So you say that for the Brookhaven?
And for the Brookhaven, the same thing, and for the Americans in 1970, again the same thing. It was a major change to introduce an independent trigger in order to distinguish between presence of a muon and absence of a muon.
I have a small answer for Witold.
Yeah.
The background was known to 30%, but the signal was 5 times bigger. That's what Dieter just explained. So the error on the background is 0.3 error on the associated to signal events, the B over AS. That was 30% error, but the signal was much, much bigger. So that didn't have a big effect on the discovery. Now, to answer the number of people who actually worked, there were many more people who actually worked than those who signed that paper. I can tell you because I was one of them as a master's student.
No. There are lots of people. I mean, I could name them by, I could nominate them easily, but I refrained from putting in the talk names. It is really true that there are lots of ideas, independent ideas, how to get control what is really happening. Very elegant models have been proposed, which was very useful in order to convince people that a new effect exists. Michel?
I want also to mention, because that's the only bubble chamber experiment, that at that time, that's mainly for young people, there was hundreds of scanning people, mostly women or students which were working 24 a day in order to scan all these pictures of Gargamel and other bubble chambers. It was also quite a lot of effort, human effort, to produce all this data.
Well, in fact, the quality of the so-called scanning girls, they were married, of course, or most of them, was really crucial for the whole thing. I mean, see, we physicists were asked then to check the dubious cases, and I mean, not only during scanning, but afterwards also during the measurement. There were many cases where you have a very short track and then an interaction. So how do you estimate the energy? By measuring the curvature of the track, it is not sufficient. So you have to do some handwork in order to get a correct energy to that. There, the physicists were absolutely necessary, and I mean everybody was down in the basement to do the work.
Can I ask you, Sergei here?
Yeah.
Where, I mean, the collaboration, was it content with some theorists, or were there any theorists who had any significant impact on your plans for the experiment?
No, there was not directly a theorist inside. However,
no, not inside. I mean, of course, I didn't expect it to be inside.
I mean, of course, the high-level people had contact to the theoretician. I mean, there was Brentke, there was Mariquet-Gaillard. I mean, they talked to each other. I mean, how often that was not always told, but at least they really made sure that we understand that we have to do something, and not to come up with a perhaps, but with a yes or no. I mean, this was not obvious, because whatever existed before was a limit of 5%, which turned out to be wrong, and another limit which was 10 to the minus 5. So nobody was really prepared for a big number.
Moreover, if I may add, I mean, there were theories without, gauge theories without neutral currents.
Yes.
On top of it.
Yes. Yeah, maybe. I mean, Carl has made a contribution to that. He can comment, I think.
Two anecdotes I could relate to the alternating neutral currents. I was at CERN in the years fall 73 and 74. And coming from Fermilab area, the rumor circulated, I'm not sure exactly how true it was, that Carlo Rubbia, who was one of the members of the HPW team, carried 2 handwritten copies of letters in his pocket. And depending on what Gargamel representative would say, he'd pull out the other one saying Fermilab did not agree. You know, the HPW did not agree with that. And the other remark I'd make that you didn't really hint to is that there was a lot of opposition from Jack Steinberger to the Gargamel result.
That's right.
And
that was a
he did not believe in neutral currents, and he was adamant about this.
I mean, just to take up the remark yesterday of Cecilia about believing, he said, I don't believe you. So, I mean, I explicitly could reject all his arguments. Nevertheless, he said, I don't believe you anyway. So, I mean, you can't do anything in that case. And he remained like that until, I believe, when it was impossible to deny it anymore.
He lost a bet.
Yes, that's right. He lost a bet with...
So very good when he had to pay out.
That's right, yeah.
Actually, once I was standing in the line to have coffee in that, the little part, and then Carlo came like a hurricane, Hi, Cecilia, have you heard? There are no neutral currents, he said. I have a letter I'm going to send. It was typical of Carlo. I mean, you are really describing him. I've had many encounters with him, so many that he thought I had a black belt in judo, which I don't have. I mean, I don't know what he was imagining, and he even asked me, "Are you looking for trouble?" And I said, "Yes, I am." And then he just walked away. Honestly, I mean, he's a very interesting person for somebody to analyze. I'm not me because I don't understand such things, but he's really very interesting.
Sergei?
Actually, in the paper by Gelman and Feynman from '58 on the V-A structure of the charge current weak interaction, there is a footnote where they they point out to the possibility of existence of neutral current weak interaction, but they say we are not going to pursue this idea further.
Well, I think at the end I should pronounce a word in favor of Rubbia.
Please do.
During the conference in Bonn, there was a parallel session, and the Gargamel data were presented there, and Fred Bullock was starting the discussion, and after the first sentence, Rubbia made his intervention, and then there was a fight between, essentially me and him, and he asked a question, I gave an answer, he asked another question, I gave another. So at the end, he was waiting outside and said, "I gave you hell, but I believe you are right."
Yes. So following Sergei's comment, it must have been Murray who wrote that footnote. He was known to do that because when Scully and Barish went to talk to Dick, he said he didn't believe in neutral currents. He said that was based on some mathematics, and he didn't really believe it. So I have to assume.
Yeah.
It's on? Okay. So I have to assume it was Murray's footnotes, and as you know, Murray's footnotes were sometimes more important than the paper.
Yes, on this remark, I think we can close the session, and thanks all the speakers.